reluctantly crouched at the starting line. Engines pumping and thumping in time. The green light flashes, the flags go up. Churning and burning, they yearn for the cup. They deftly maneuver and muscle for rank. Fuel burning fast on an empty tank. Reckless and wild, they pour.
In this demo, we have 4 different solutions that will each demonstrate a kind of luminescence called fluorescence.
We have in Beaker 1, tonic water. In Beaker 2, we have a fluorescein solution. In Beaker 3, we have an eosin Y solution. And Beaker 4 contains a rhodamine B solution.
As you can see, the tonic water is clear under the white classroom lights. Each of the other solutions appeared colored under this light as they absorb and reflect different wavelengths of light in the visible spectrum, which is 400 to 700 nanometers.
Now under black light, each solution exhibits fluorescence. The black light emits UVA light, which is 320 to 400 nanometers. As the solutions absorb the UV light, their electrons become promoted to higher states.
As the excited electrons fall back step by step to the ground states, they emit photons in the visible spectrum. This is true because the light that is emitted can be seen by the human eye.
By this trial, it can be inferred that the molecules that fluoresce in each solution have absorbed peaks in the UVA section of the electromagnetic spectrum, and each has its own corresponding peak in the visible area of the spectrum.
Now, as you can see, the tonic water emits a blue light. The fluorescent solution emits a kind of lime green sort of light. The eosin Y solution turns orange, and the rhodamine B keeps its purple color.
These solutions each demonstrate fluorescence because they only emit light when in the presence of an exciting source, which is the black light.
Once again, these solutions are emitting light and not reflecting the UV light from behind it.
This next demonstration teaches the same concepts of chemluminescence seen in the cool light demonstration. However, this demonstration lasts longer and produces different wavelengths of light.
The basic reaction again is the oxidation of luminol by hydrogen peroxide. However, the presence of calcium, also known as fluorexon, prolongs the reaction. Here we go.
The presence of calcium prolongs the reaction because rather than release its energy in the form of light, the luminol in the excited state transfers its energy to calcium.
As the energy is transferred to the calcium, the excited calcium slowly releases its energy in the form of emitted light as it returns to its ground state.
The main reason for this slow release of energy is calcium's ability to self-quench. This creates a long oxidation potential that prolongs luminescence.
The luminescence seen here is again classified as chemoluminescence because it takes place as a result of a chemical reaction and little or no heat is produced.
Alright, we're good, thank you.
Dude, this stupid steering rod didn't do anything for it.
In this demonstration, the brilliant light produced is a result of the oxidation of luminol by hydrogen peroxide in the presence of the potassium ferrocyanide catalyst.
The chemoluminescence of luminol was first discovered by H.O. Albrecht in 1928. He determined that 3 conditions must be met for chemoluminescence to take place. The first condition is an alkaline solution. The hydroxide ions present prep the luminol to be oxidized by hydrogen peroxide by making the luminol into a dianion. This is necessary for any reaction to occur.
The second condition is the presence of an oxidizing agent, in this case hydrogen peroxide.
The third condition is the presence of a catalyst, which is the iron 3 cation. In this case, potassium ferrocyanide is used.
The hydrogen peroxide oxidizes the dianion from form of the luminol into the amino phthalate ion that is in an excited state.
These excited aminophthalate ions quickly fall back to their ground state. Light energy is released during this jump from high to low energy.
This emitted light has a wavelength of around 425 nanometers, which, as you can see, is blue in the visible spectrum.
As the reaction is carried out, it can be enhanced with the addition of more hydrogen peroxide and small amounts of potassium ferrocyanide. As the solution hits the Erlenmeyer flask at the bottom of the setup, there is more potassium ferrocyanide which excites the solution.